Good morning, good afternoon, or good evening, depending upon where you are in the world, and welcome to today's webinar, Leveraging Multicore Platforms for Mixed Criticality Systems, brought to you by Tech Online, Wind River, and broadcast by AspenCore. I'm Chris Keach, and I'll be your moderator today. We have just a few brief announcements before we begin. First, the slides will advance automatically throughout the event. You may also download a copy of the slides by clicking on the green folder icon located at the bottom of your screen. You can participate in our Q&A session by asking questions at any time during this webinar. Just type your question into the Q&A text area located to the right of the presentation window, and then click the Submit button. Please note that we'll try to get to as many questions as we can in the time that we have left at the end of today's program. However, if we're not able to get to your individual question today, someone will get back to you after the program is over. Also at this time, we recommend that you disable your computer's pop-up blockers. This will allow the slides to advance automatically throughout the event. And at the end of the webinar, we will ask you to complete our feedback form. Your feedback will provide us with valuable information on how we can improve future events. You can also launch the survey at any time by clicking on the red survey button at the bottom of your console. And if you're experiencing any technical problems, please type your issue into the Q&A text area, and we will be glad to offer one-on-one assistance. And now, on to the presentation. Leveraging Multicore Platforms for Mixed Criticality Systems. Discussing today's topic is Martin Koning, Vice President and Wind River Fellow. As the head of Wind River Technology Office, one of Martin's key responsibilities is to help forge the path for companies' technology directions, as well as inspiring, accelerating, and enabling Wind River's customers and employees. It's with great pleasure I now turn this special session over to Martin to begin. Martin, take it away.
Thanks, Chris. So this is a presentation for computer scientists, product managers, and technology leaders. I'll be making the case for leveraging an embedded hypervisor in your embedded system to enable your system architecture to evolve into the future. We'll be zooming out and considering some mega trends, and also we'll be zooming in to computer architecture and touching on SMP OS internals. But first, a Moore's Law slide. So I'm pretty sure at least one other technology presentation has kicked off with one of these. Amazingly, it's pretty much still holding. So let's have a quick tour. It is interesting to look at this once in a while. So let's start with the red curves, the lowest one there, the power being fed into a silicon chip. It's pretty well flattened out, and you'll note this is an exponential scale. So that means we're not getting more power into the chips, and we're also not getting higher speeds. The megahertz has really flattened out as well. And interestingly enough, a single core thread performance is also now flattening out. We used to think of Moore's Law as giving us more performance, even though it doesn't really say anything in the law about performance. We had an expectation of performance. And that's not holding anymore. And some people call that Moore's gap. And the reason is that the silicon designers, processor architects, are out of tricks, out of order execution and speculative execution, branch prediction, and adding transistors to caches. These things don't help us anymore. And yet Moore's Law ticks along and gives us exponentially more transistors every 18 months to 24 months. We're still doubling. So where are those transistors going, and how are we going to be using them, especially for embedded silicon? So obviously we're seeing SoCs, where we're integrating the memory controllers and having a certain amounts of flash and SRAM, and we're pulling in board components such as GPIO and PWM, DMA, even buses and fabrics are getting pulled into the SoC. And we're getting features from big iron silicon, non-embedded silicon, virtualization, integrated GPUs. These are becoming very powerful full computers, and they're getting what used to be desktop and even mainframe features such as virtualization. However, these are all fixed size building blocks, and they're in there now. So that means that the future for embedded silicon will continue to be adding cores, and it's that other bottom line on the Moore's Law slide I started off with. That will continue to climb. So what does that mean for software architecture? Well, it means we have opportunity to integrate discrete systems right into the multicore SoC. We'll be seeing multiple OS instances running in a single processor more frequently, and that those OSs will have different core values. Some might be best effort OSs that are doing some management capability, and other OS instances could be real-time OSs or safe OSs that are doing some time-critical or safety-critical application. And now they're being integrated, and we call that a mixed-criticality system because you have both. You have the critical function and the non-critical function in the same processor, in the same SoC. And this also means we're going to see a bigger software building blocks being integrated into these systems and increase system complexity because you have entire operating systems being assembled into solutions inside a chip. And that itself brings additional manageability requirements and more software to do those manageability functions, such as updating, tracking, health monitoring. And we're seeing basically a move towards loosely coupled systems existing inside a chip. So the kinds of software that people are integrating, it's very diverse. There is real-time software and best effort software that I mentioned, but there's also free and open source software that's coming into the systems and being integrated with proprietary software. And the licenses for that software can vary. It could be a viral license like the GPL, which might warrant some sort of a license containment technology because that software can't be combined with, for example, non-viral or commercial licensed software. The mixed integrity software and certified software that I mentioned. You may have software that wants to run directly on hardware in a bare metal partition of some sort, being combined with other OS instances and even containers that are running on those OSs. And meanwhile, the software could have been architected originally to some monolithic, tightly coupled software architecture, and while other pieces are perhaps separated out into partitions and can be more easily put inside a fault container, for example. And of course, there is operating system software that likes to have very specific, shall we say, brittle hardware resources provisioned to it versus OSs that can discover their resources at runtime and are more, shall we say, plug and play. And those OSs come with BSP, the brittle ones come with BSP constraints and requirements that need to be provisioned by some underlying hardware management layer so that they can be integrated into a multi-OS system. All this diversity in software, it's really motivating us to think more about element separation. When you integrate these components, these large systems into partitions with some container technology or some fault partitioning technology, you get a lot of benefits. And there are many reasons to do that, to partition these software assets into these separate partitions, such as you may have to do it because of the core attributes of the software. So real-time versus best effort or certified versus non-safe. You may want to protect the data in the code or even credentials that that runtime code has so that other parts of the system don't have access. You may need to partition resources to that software because it has a very specific resource requirement to meet a deadline or to perform its function. You may simply want fault propagation prevention so that if a piece of software fails, you have a box around it and it's not going to take down the rest of the system that's running inside that multi-OS, multi-application SoC. You may have a piece of software that's stable. And the thinking here is that, don't touch it if it works. If it has a nice API and it's doing its thing and it's been hardened or certified and you can use it as it is, put a box around it and use its interface and integrate it and extricate value out of that as a separate element that can be a building block. And the corollary to that is if you have a piece of software that is evolving a lot, it's also nice to separate it out so that you can update it or patch it or add features to it and replace just that element when you do that. Org chart is another reason to have element separation. Now, obviously, we don't want our software architecture to reflect our org chart. However, sometimes it is helpful to have an agile team, for example, that owns a software element and can release it along their own cadence and update it when it's necessary for them. And that means that they would like to control that partition or that piece of software and even push it out in some cases to deployed systems using the so-called CI/CD methodology. Live update is another example. If it can be updated live in a deployed system, why not? Maybe it should if it can. So there are many reasons that it's helpful for us to pursue a loosely coupled software architecture using element separation. And there are more reasons too. For example, you may want to have some redundancy in your system. Perhaps it's 1 + 1 spared, or it's load shared. You might have specific hardware that's mapped into a partition that isn't mapped into other partitions or an OS, so you need to keep those things separate. You may be able to horizontally scale within your product line by having different SKUs of CPU and having partitions that are execution engines that can be instantiated multiple times for the CPU SKUs that have more cores. Would be a good reason to have a loosely coupled element-separated software architecture. And similarly, you might have some shared services that are used by those instances. Now, all of this gives you some architectural flexibility and some operational flexibility in that you can put in place a framework of multiple software elements that you can add to, you can replicate, you can manage, both at the development level, but additionally at a deployment level for deployed systems. It gives you entities that can be managed basically. And so you can even change resource scheduling on the fly for elements that are broken out. For example, in an aircraft that is taxiing or parked or taking off or flying or landing, it's helpful to be able to change the frame scheduler for the elements for the avionics system based on the state. And so when you break that out and you have resources for just that part of the system, even though there might be other parts that are for maintenance or that are non-critical elements in the system, but just for that part, you may need to change the resource profile on the fly so that it can meet its deadlines. And having those separate elements allows you to do that. And finally, just having clean separation between software components is just the best practice for managing system complexity. We really don't want to have a tightly coupled monolithic system that comes together as a big, shall we say, blob. All right, so these loosely coupled systems, nothing new, and they come in various forms. You might have multiple computers on a network that are collaborating to be a system, and in fact, some avionics systems are constructed this way. You might have multiple boards in a rack. For example, blades in the OpenStack system that are compute blades or management blades in a cloud node. You might have multiple processors on a board or even in a chip that aren't sharing a memory system but are collaborating on a function in some loose way through an interconnect. Maybe they're communicating sequential processes, sort of model like a sonar array or something like that. It's still a potentially a loosely coupled system in that they might individually reboot or have individual software loads on them and send messages between them. And finally, you could have multiple virtual machines on a hypervisor and sort of polymorphic to the other ones using virtualization technology that is also a loosely coupled system. And that's what we're going to be talking more about today. So virtualization has been around a long time, and embedded systems programmers and architects are a very conservative lot. You know, we like to be very careful about the technologies that we hitch our wagon to. And virtualization, though, has been around since the 60s. You know, it was developed by IBM originally as a mechanism to safely share mainframe resources. And they enumerated two types. The type 1 hypervisor, which is a native hypervisor in that it runs directly on the hardware. So it's not using any other APIs except for hardware. And type 2 hypervisor, it runs over top of an operating system. So the underlying OS is extended with some virtualization technology that provides the illusion of a platform, of a hardware platform to the guests. But there is an underlying OS in a type 2 hypervisor. So embedded hypervisors tend to be a little different from IT hypervisors, which are traditionally type 2. I mean, there are some IT hypervisors that are type 1, but embedded hypervisors are also different because they are almost always type 1, unless they're hosted by a real-time OS. They provide fine-grained resource provisioning so that you can put very specific amounts of hardware resources, compute, CPU, memory, devices, the very fine grain into the guest. And they are very small footprint themselves. They tend to be entirely written using real-time programming techniques. And you know that's necessary because they might be running a real-time guest in an embedded system. That's typically what you have is some concept of time required in the guest. And the good ones are developed to safety certification standards so that you not only can use this embedded hypervisor in a real-time system, but you could also potentially use it in a safety-critical system. And one of the interesting differentiating features of an embedded hypervisor is that they prioritize the elimination of interference channels, and I'll talk more about interference channels on the next few slides, over performance. So they would rather have very hard separation between partitions than run faster or have more throughput. And that's unlike what you would normally see in an IT hypervisor, where yes, they're concerned about security, but they're really trying to run as much traffic, if it's transactions or network traffic, or maybe it's acting as a data pump, through that hardware as possible over determinism. So interference channels, they can affect both safety and security. And so let's just double click a little bit more on the interference channels. You know, I like these dense definitions of safety and security. Safety protects you from the system, and security protects the system from you. And when we talk about safe software, we really are talking about software that needs to execute exactly the same way every time it runs. And we use words like determinism, real-time, time and space partitioning, order one algorithms, worst case execution time when we talk about safe software. Secure software tends to be software that can't be influenced by other software because such influences can leak data or could allow manipulation of code that might enable future leakage of data. Both of these categories of software, both safety and security, can benefit from element separation using strong fault containers, strong containers. Interference channels in general are a huge problem for critical systems, and they need to be considered whether the interference channel is caused by hardware or by software. Turns out that sharing hardware or sharing software need to be done very carefully for both safety and security reasons, as we discovered with Spectre and Meltdown. Let's look at a few examples. On the hardware side, an interference channel could be caused by a shared memory on a shared bus that maybe one guest is accessing very heavily, and that's causing maybe some denial of service or some slowdown of access for another guest that can affect its performance. Similarly, you could have some interrupts coming in that are being triggered by one guest that are stealing cycles from a hypervisor if those two guests are sharing a core. And similarly, you could have, on the software side, you could have an OS that's being shared by two software elements, and that could be an interference channel. If one application is calling down into the kernel, and that kernel is taking a lock, and then you have a higher priority application preempting it, and it tries to call down into the kernel and take the same lock, well, it's going to be deferred and blocked, and you have a priority inversion situation when that happens. So these are examples of interference channels that are caused by software or by hardware. If the silicon designers were able to design the ultimate software for safety critical systems, we'd probably ask them for something like this. We would want to have a multi-core chip that had private memory per core for the code and the data that it's going to run, private cache for that memory, and it's not going to want to use any shared lower level caches, some deterministic transfer of data from that core's memory to other cores for IPC and interaction. Maybe that could be implemented using dedicated FIFOs or DMA with some quality of service guarantee, reflective memory or switch memory, something like that would be the way to go. Also, if there are shared devices or shared resources, we would want to have some kind of arbiter that provides a guaranteed throughput and some guaranteed response time for the cores that are in that safety critical system. And finally, of course, you always need to have some distributed clock so that you can synchronize your cores when you need to, so that they can perform. They can be orchestrated to perform things at exactly the same time. It's possible when there are hardware interference channels to mitigate those interference channels using software techniques. It might seem that some of these techniques are extreme. However, they are common practice in safety critical systems. Such systems are prioritizing the elimination of the interference channel over performance, and they would rather it run slow and run exactly the same way every time it runs than have some variability and miss a deadline. Even though it might make it 99.999% of the time, that's not good enough for a safety critical system. It's about the worst case, not the average case for safety critical systems. So they might do things like schedule virtual machines across the cores so that they can't run at the same time, so that there can't be a hardware interference channel caused by shared hardware between those virtual machines. For example, if you had a certified virtual machine running a safety critical application on core 3, you may not want or be able to run a best effort operating system on cores 0, 1, and 2 at the same time. So what you would do is have a synchronized scheduling through a hypervisor feature so that you don't run the SMP OS running on 0, 1, and 2 when you're running the safety critical application on core 3. And in addition, you might just want to flush out any or partition or even disable the any shared caches so that there can't be any hardware interference through the cache either. So that's not something that you would think about doing when you're trying to run as fast as possible, but it is something that you would leverage in a safety critical system when there's a mixed criticality scenario in that system. And then there's this. Let's just zoom out a little bit and go back to another law, good old Amdahl's law. Now, Amdahl's law does have some constraints, and it's really originally was speaking about scenarios where you're adding cores of the same size, and it doesn't really consider using parallelizing computers to exploit concurrency. But for traditional programming model where you are adding cores to your system, Amdahl's law teaches us that that the parallel speed up is going to be inversely proportional to the amount of serialization in the system, and that all systems have some serialization. In fact, if you look at a system that has 5% serialization, let's look at the center bars here, which is comparing the performance, the theoretical performance that you would get out of a 1-core versus 5-core versus 10-core versus 32-core system that has 5% serialization. With 5 cores, you might be getting 4-point-something X, which is pretty good compared to your 1-core. But with 10 cores, you might only get, say, 7 cores of performance. So, that means you paid for 10 and you only got, well, let's say 6 or 7. So you're not exploiting the value that you're paying for, or the silicon value. And the reason for this is the serialization. So why do we care, and what can we do about it? Well, we care because SMP operating systems have spin locks, and spin locks are the cost of concurrency. When a single core calls into the kernel, it has to take some locks, and that's what you pay to enable concurrency in an SMP system. You can't just lock interrupts or set a flag, I'm in the kernel. Instead, you have to coordinate the access to the shared data structures with the other cores. So the simplest SMP kernel can be implemented with a single giant spin lock. So if that spin lock can be taken recursively, it can't deadlock even against itself, but that doesn't enable any concurrency. A medium-grained locking strategy in an SMP kernel, that enables concurrency with a modest per-core performance penalty, but that's not going to scale to higher numbers of cores due to Amdahl's law. And then finally, fine-grained locking systems, that have many locks, these have performance issues per core, but they do scale well due to less serialization. So with fine-grained locking, you're taking many, many locks to perform even a single system call on a single core. So your system call performance goes down because of that. But because the granularity of the locks is less, it's possible that you can have more concurrency because more of those locks are available to other cores to take at the same time. So, but really none of these options are attractive. You either pay performance-wise in the single core case, or you aren't exploiting the parallelism in your system, and Amdahl's law is going to bite you. So there is another way, and that is to consider having multiple operating systems in that SoC. And since we are going to have many cores, even in embedded systems, this motivates us to think about element separation and multi-OS systems and hypervisors in embedded systems. And we use the hypervisor to run multiple uniprocessor and or SMP OSs across those cores. The hypervisor itself, of course, has to be implemented using lockless real-time techniques. And that means that it typically uses send, receive, reply, and threads to block, not SPID locks. You want to leverage virtualization so that these OS partitions are hard fault containers. And these hypervisors typically provide some sort of safe IPC mechanisms between the OS partitions. They have to be made small and certifiable to focus on security. And the reason they need to be small is so that they are certifiable. It's incredibly expensive to certify software. But if you do these things and you break up your system into these multiple OSs that don't share global data and don't serialize on that global data, then these systems can scale to hundreds and potentially thousands of cores. And so that's the goal here, is to put in place an infrastructure that allows us to continue to use the embedded processors into the future as they become available. We're getting so many requirements on software that having some lower level infrastructure to create an integration platform is becoming increasingly important, even in embedded systems. We can't just architect the whole thing as one big system anymore. There are too many moving parts and too many requirements. So systems, including embedded systems, are becoming integration activities, and they're being assembled from these larger building blocks. And the requirements that drive that and drive the need to have these fault containers with OSs instead of sharing an OS. Yes, there's this multi-OS scenario due to Amdahl law I just covered, but there's also this need for redundancy and resilience to increase reliability and availability so that you can have more than one of something and have those somethings be more self-contained, so that they can be instantiated and they can be replicated as elements that provide the APIs that their applications need as their own bound entities. And there are requirements for element separation, as described earlier, to support continuous integration and deployment and to reduce fault propagation. So that's another reason that you might want to have strong fault container technology. And of course, the large amounts of open source software that's coming into these systems, they need to have a box put around them so that they're not causing any software interference channels into the rest of the system. And the hypervisor and fault containers and the fault containers that the hypervisor provides you help you with that. So at Wind River, we've been using this terminology, a real-time island and safety island, to describe the portion of a multi-OS system that deals with real-time and safety, respectively. So the idea is to leverage Linux or Android or even Windows where it makes sense, whether for containers or analytics, machine learning, or middleware and application frameworks, and to use an RTOS where it makes sense for performance, determinism, or certify-ability. By leveraging virtualization for system integration with a hypervisor, we think this will increase the development velocity because you're assembling systems with larger building blocks and you're only concerning yourself with the real-time nature or the safety nature of just the portion of the system that needs to be real-time or safety. And we think also this will ultimately increase resilience for the real-time and the safety parts of the system. It'll provide us increased architectural flexibility because we now have system integration technology to integrate open source and also to partition out elements. And that will allow us to have increased portability so that we can bring applications in and we can even reuse them more easily from one product iteration to the next. So what does that look like? What does the real-time island and safety island look like inside? Well, basically, you take virtual machines and you allow them to be used in a collaborative fashion easily. So that, for example, an RTOS-based application can read or write files from any file system supported by a best effort OS like Linux. That allows a small real-time kernel to read or write exFAT or access its Wi-Fi driver suite when it needs to talk over radio or Bluetooth. And instead of pulling those capabilities into the real-time environment, instead you turn that around and say, well, you know, Linux has drivers for everything. Let's leverage those. Let's make them available for the non-real-time parts of the system. And many of those interconnects tend to be non-real-time or non-safe anyway. So for those situations, we will just reach across and use the stacks over on Linux because those functions are non-real-time and or are non-safe. So that's the motivation thinking and the way that these collaborative systems will be constructed more in the future so that you're only doing the real-time portion and or the safety portion on the real-time and safety OS. With an architecture like this, you can see that there's some common DNA across these diverse silicon configurations. You might have multi-OS, multiple virtual machine system running on a hypervisor that's single core. And the RTOS is preempting the Linux virtual machine. And so now you've got real-time with Linux because the hypervisor is real-time. You might have the same thing on a multi-core system where you have the RTOS running on its own core beside Linux. Same software architecture fundamentally, but now maybe the performance profile is different because you're exploiting the cores individually. And that same architecture scales to bigger multi-core as well. So when you look at the requirements that you want to have to achieve this vision, you need an embedded hypervisor that, yes, supports hard real-time guests and is hard real-time itself so that it can do that, that enables certification and is certifiable itself so it can support safety applications. Device sharing is very important for these systems. For example, in an automotive application, you may want to have cluster information and critical information overlaying IVI or sharing in some way the GPU if they're separate displays. You want to have robust partitioning that minimizes the interference channels mentioned. And of course, you want this to scale so that when you put in this architecture into your portfolio that it's a little bit future-proof, that you can scale up the number of cores over time and enjoy the architectural and operational flexibility by having that layer underneath. In addition, the hypervisor should provide some more features. It should enable you to have silicon independence, not just of CPU skills, but even processor architecture so that you can have some portability where needed. Perhaps your product line has very high-end and very low-end configurations, and the processor architecture needs to change for the low-end or for the high-end. Ideally, a hypervisor would support more than one processor architecture to enable you to carry it forward across those different chips. It should support both UP and SMP guests. Fractional core scheduling. This is where you say, I want to have half a core to this virtual machine and a half a core to that virtual machine. And so that you can have more guests than cores. So that your element separation strategy can actually map to your deployment hardware where you have less cores than guests. It should support VM preemption so that you could even run a real-time virtual machine on the same core as a best effort OS. Ideally would support unmodified guests so that you could boot in a virtual machine OSs like Android or Windows without having to paravirtualize them. And enabling shared device access or individual device access is also something a hypervisor should help you with, so that you could have, for example, one PCI device mapped into one virtual machine and another PCI device on the same PCI bus mapped into a second virtual machine, and each one doesn't see the other's devices. And that's done using PCI bus emulation, so that the discovery process and the mapping process only gives the guests exactly what they're provisioned to have. And it really should, the hypervisor should really support direct interrupts, so that you can enjoy native performance when the virtual machine is running and an interrupt comes in. The interrupt should be mapped directly in hardware to that guest. And that's a feature supported both by most modern Intel processors and also ARM, such as the Cortex-A53. All right, so in summary, let's just sort of recap the argument to leverage an embedded hypervisor in an embedded system. You know, Moore's law plus Moore's gap teaches us that multicore SoCs will become pervasive even for embedded systems. And Amdahl's law teaches us that multicore SoCs will really need to run multiple OS instances to avoid contention due to OS serialization. And we're also seeing trends towards loosely coupled systems assembled from independent software elements with varying core values, you know, like diverse software, that motivates us to have multiple OS instances in a single OS, in a single SoC. In addition, safety requirements motivate certified real-time software at the lowest level of the system because the requirements flow from the bottom up there. And the trend of open source really becoming Linux open source. You know, many open source projects now only build and support Linux, whereas in the past there was more a broader range of OSs that you could configure them for. So that really motivates the integration of Linux into embedded systems. And having a hypervisor to help you with that, pulling that into a and creating a mixed criticality system is highly valuable and increasingly valuable. And the requirements for software architectures to be flexible over time. That motivates the introduction of a silicon-independent hardware abstraction and resource provisioning and resource management layer, so that you can decouple the hardware more from the elements of software that are being integrated into that system. And the trend towards workload consolidation that's enabled by multi-core devices, that motivates a virtualization-based integration technology that can provide strong time and space partitioning. So all of these things motivate a real-time certifiable hypervisor in an embedded system. So, you know, my question to the computer scientists and product managers and technical leaders in the audience is to consider whether their software architecture can benefit from having this layer, so that it can be more flexible into the future, so that you can extricate more value out of the software assets that you have by hardening them and using them as larger building blocks, because they're separated out as elements. And if you think that's valuable for your system, you know, please consider calling Wind River. We think we can help with that. So thank you very much. Chris,
all right, well, thank you, Martin. Thank you, Martin, for a great presentation. As a reminder, please fill out the feedback form that will open up at the end of the show. Thank you in advance for filling out the feedback form. Your participation in this survey allows us to better serve you. We're now going to move on to the question and answer portion of our event. As a reminder, to participate in our Q&A session, just type your question into the text box located to the right of the presentation window, or click on the Q&A icon at the bottom of your screen, and then click the Submit button. Please note that we'll try to get to as many questions as we can in the time that we have left. If we're not able to get to your question today, someone will get back to you after the program is over. So let's go ahead and take a look at our first question. First question for you, Martin. What are the differentiating features of Wind River's embedded hypervisor technology?
Well, I think the interesting thing with Wind River's virtualization technology is that it's really a unique combination of all the must-haves and should-have requirements that I listed at the end of the presentation. It's also available on most single and multi-core hardware processor architectures and chips that are used for real-time and safety applications across, many vertical markets, avionics and industrial, for example. The technology comes with full buildable source code. It's hard real-time, lock-free, certifiable. You've got static configuration options that can use qualified tools for safety applications, and also dynamic configuration scenarios if you're doing real-time systems. And of course, it comes with the Wind River, brand, leading embedded systems company that has a rich history and proven experience with such software.
All right, thank you, Martin. Another question here for you says, what kind of system should we not use an embedded hypervisor for?
Right. Well, hypervisors can achieve zero overhead. If you're using direct interrupts and direct mapped hardware. However, you typically want to have a hypervisor because you have more than one virtual machine in mind, or where you have some manageability feature from the hypervisor. And in scenarios where the resource partitioning is static and there are real-time or safety requirements, an embedded hypervisor is appropriate. But if you have a non-real-time, non-safety application, and perhaps you have increased manageability requirements around dynamic execution, then I think an IT-style hypervisor is probably what you want. An example of those requirements are things like hot swap hardware, core balancing across virtual machines dynamically, dynamic VM management in general, VM suspend, resume, VM migrate. These are more IT hypervisor functions that you might find in a data center where you want to prioritize manageability and throughput over low latency and high determinism. So that's what they're primarily designed for. So I think an embedded hypervisor would not be used when you have those kinds of IT requirements.
All right, thank you, Martin. Another one here says, what services does a hypervisor provide, and can a hypervisor be added to an existing system?
A hypervisor can be added to an existing system, depending on the hardware that it runs on, because you can create a virtual board, shall we say, on a hypervisor. You can provision it, the addresses of the memory and the devices that are mapped into that, so that it can meet the requirements of an existing system. Of course, if the existing system has very arcane hardware binding, that can be difficult without doing some sort of emulation in the hypervisor. But yes, the idea is that unmodified guests and unmodified bare metal applications can be pushed into virtual machines and run on a real-time embedded hypervisor.
All right, thank you, Martin. Another question here that just came in for you. Can you comment on hypervisor security certification, RMF versus common criteria EAL6 certification?
In general, hypervisors are becoming increasingly certified with various certifications. I think that if you want to deep dive on a very specific part of certification for a certain application, that's something that I would want to, shall we say, punt to our certification experts. And I'd like to do a follow-up on that one with you.
Thank you, Martin. Another one here says, can you comment on the 178 DAL or DAL-A verification of a hypervisor that requires the hardware virtualization it relies on to also be certified?
We have achieved 178 DO178C level A with our hypervisor technology, and that, well, I mean, we've provided the criteria to certify a system. I mean, it's really the hardware plus the software plus the application that allows the system to become certified. And so we provide the collateral for the multi-core runtime environment, DO178C level A. The customer has to also certify their application, and the hardware vendor provides their criteria as well, and such systems have been certified.
All right, thank you very much. Another one here for you says, can you give some examples of systems that have successfully used an embedded hypervisor to do workload consolidation and or mixed criticality deployment?
So workload consolidation has been successfully used in industrial products where you're taking a best effort OS, such as Windows, doing management and data processing, and you also have an RTOS that's doing the real-time sensing and actuation. For example, in PLC devices that are used in factory automation. Mixed criticality examples are avionics and automotive systems that have safety critical systems and maintenance or management systems both executing on the same certifiable embedded hypervisor. So this can be a VM containing a best effort OS like Linux or Android beside a VM that has a certified RTOS-based application. It can also be a certified RTOS-based application beside a non-certified RTOS-based application, both in VMs on an embedded hypervisor. So yeah, those are the examples for both workload consolidation and mixed criticality.
All right, thank you, Martin. Another question here came in, says, what kind of tools exist to measure the performance impact resulting from the use of a hypervisor?
Well, for Wind River operating systems, we have profiling tools, and we also publish the overhead for any hypercalls that are generated down to the hypervisor so that the worst case execution time can be calculated. You know, typically system engineers are very careful about calculating that, and they need those numbers in order to guarantee that they're going to meet their runtime profile. So yeah, we provide published numbers, and we also provide profiling tools for our runtime environments.
All right, thank you, Martin. Another one here says, I guess it says leveraging multi-core platforms for mixed criticality systems. It looks like just I guess they want to know more about that.
I think I don't understand that question actually, so I think we'll just pass on that one.
Okay, very good. Move on here to another one. Let me take a look and see if we have any other questions. Real quickly, just wanted to tell our audience if you'd like to ask a question, just go ahead and type your question into the Q&A text area, click the submit button, and we'll take a look. Looks like we're out of questions for right now. Martin, do you have any quick final thoughts before we go ahead and sign off?
No, thank you very much, Chris, for moderating the session, and I really appreciate this opportunity to give this presentation.
All right. Well, thank you, Martin, again, for a great presentation and Q&A session. And that looks like all the questions that we have for today. If we didn't get to your question, someone will get back to you after the program is over. For more information related to today's webinar, please visit any of the resource links available in the green folder icon at the bottom of your screen. And within the next 24 hours, you will receive a personalized follow-up email with details and a link to today's presentation on demand. Once again, we'd like to thank our audience for attending today's webinar, Leveraging Multi-Core Platforms for Mixed Criticality Systems, brought to you by Tech Online and Wind River. This webinar is copyright 2018 by AspenCore. The presentation materials are owned by or copyright by Tech Online and Wind River, and the individual speaker is solely responsible for his content and opinions. On behalf of our guest and Wind River, once again, my name is Chris Keach. We'd like to thank you for joining us, and we hope you have a great day.